Is a very important technique in machine learning and data science. I'm sure most of you have used logistic regression in your projects. Along with the practical knowledge of how to use logistic regression, I think it is also important to know the statistical underpinnings of logistic regression. For example, how does maximum likelihood estimation work? What is the interpretation of these coefficients beta? After building a logistic regression model, how do you know that this is a good model? What are the different diagnostics that are available for logistic regression? If you're looking to answers to some of these questions, this is the video for you. Hi, I am Sachin, co-founder of Accelerate AI, and in this video, I'm going to talk about logistic regression and its mathematical underpinnings. So we'll talk about the premises of logistic regression. We'll talk about the logistic function. Then we'll see how maximum likelihood estimation is used to estimate the parameters. We'll look at the coefficients and understand how to interpret those coefficients. Also very important is we'll understand what are the different model diagnostic that are available for logistic regression. Logistic regression is primarily used for classification. So we'll look at the different classification metrics for logistic regression, and in general, we'll talk about the ROC curve. We'll understand how that ROC curve is drawn. This is something which I was initially confused a lot about. Also, when our data is imbalanced, gain and lift chart can be very helpful. So we'll talk about those. And at the very end, we'll talk about how to build logistic regression model in Python. So there are many scenarios where the output or the outcome is a dichotomous variable. It's a yes, no, pass, fail, click, no click, buy, no buy kind of a scenario. Let's take an example. Say an insurance company wants to see if age, vision, driver education, gender, these could be used to predict whether the person had an accident in the past. We, if we can see, linear regression will not be able to do justice to this kind of a problem. How do we model this? One way to model this is to find the relationship between these variables like age, gender, vision, and so on with the probability of the accident. So that's shown in here. This is what is known as the sigmoid curve as well. So to model these probabilities, the logit function is what is used. Probability P of an event can be modeled using the sigmoid function. The sigmoid function Sz is defined as 1 by 1 plus exponential to the power z, and it has a S curve if we plot this. The sigmoid function maps real number to the interval 0, 1. If you want to do a reverse mapping, we can do that as well using odds ratio. Odds ratio is defined as P over 1 minus P for a binary outcome, or P becomes odds ratio by 1 plus odds ratio. In binary logistic regression, when we are trying to fit a model, uh, we are looking at this probability. By some algebra, we can show that probability will become exponential raised to the power of linear combination of all the variables x1, x2, and so on, divided by 1 plus e to the power these linear combinations. We can take log on both the sides, and then the function reduces to log of odds equal to a linear combination of all these variables x1, x2, and so on. Also, since this is a statistical relationship, there will be some error. We add the error term epsilon here. This function is known as the logit function. Logit function stands for logistic probability unit. In general, these kind of functions are also known as generalized linear model. In generalized linear model, the error terms may not be normal. However, there exists some kind of a transformation. With that transformation, the function reduces to a linear relationship. In logistic function, the link function is the logit function. So how do we estimate these betas, the parameters themselves? In logistic regression, we are trying to do is estimate the conditional probability of the event. Given the variables x1, x2, and so on, we want to know what is the probability of our outcome. So logistic regression, or the logit function, is what is used to model this nonlinear relationship. Before we go into the parameter estimation, we have to look at some of the assumptions. As we said, the outcome must be a binary outcome, 0 or a 1 is how it is typically uh, shown. We also have to have the independence of the errors, and in general, each of the experiments or trials or the data points should be independent of one another. Also, there should be no ambiguity with the output. It's either a pass or a fail, and we have to know that correctly. Also, there is an assumption of linearity in the logit. So after we have the logit form, that has to have a linear relationship with the outcome. And finally, we have to have perfect multicollinearity absent in dependent variables, any subset of the dependent variables. We can understand that ordinary least square method, which is used in linear regression, cannot be used here for estimating the parameters because the errors are not normal. Also, they are inherently heteroscedastic. So the parameters are estimated by a method known as maximum likelihood estimation. We'll see what that maximum likelihood estimation is. Maximum likelihood estimation essentially answers the question, given the data that we have observed in our sample, what probability distribution or the model parameters will maximize my likelihood of observing such data. So let's look at this chart here. So we have the data distribution given by this black histogram. Now we want to come up with the probability distribution such that it maximizes our chance of getting that kind of a data. So we'll have these different probability distributions shown by these different colors. The distribution which is in the red line is the one that maximizes our observed data. So that is the uh, estimated probability distribution. So we have to estimate the parameters of that particular probability distribution. So in maximum likelihood estimation, we are trying to maximize the conditional probability of observing this data. Now we have the probability, the conditional probability given by P of that event of success y equal to 1 conditioned on Z, which is a function of all these betas. Because we have the data given here, the parameters are not the x's but the betas themselves, which we are trying to find out. Let's represent that by pi of z. So pi of z becomes odds by 1 plus of odds, and which is given by this particular equation, as you can see on the screen. In case of logistic regression, we assume that the distribution is a binomial probability distribution, which means each of the outcome is a Bernoulli trial. So the probability or likelihood of Bernoulli distribution is given by pi z raised to the power 1 minus yi into 1 minus pi z raised to the power 1 minus yi, where yi is the outcome of the ith event. If we have n observations in the data set, then we have to calculate the joint probability, the probability of observing all of those data sets. The joint probability, if each of those are independent, will be given by a product of the individual probabilities. This product of individual likelihoods is known as the likelihood, overall likelihood. Now, handling these many small probabilities can be tricky and unstable because of rounding errors and so on in computers. So it is common to restate this problem using the log on both sides. So the left hand side is called log likelihood. The right hand side, instead of multiplication, now becomes a summation of each of these. Sigma of I equal to 1 to n of yi into log natural of pi plus summation of 1 minus yi into 1 minus log of pi of z. So we have to estimate these parameters. We can maximize the log likelihood. Usually in practice, the negative of the log likelihood is taken and that is minimized. Now to minimize this negative log likelihood, we can take the partial derivatives of the negative log likelihood and with respect to each of the parameters beta naught, beta 1, beta n and so on, and then equate all of them to be 0. In general, negative log likelihood is also called cross entropy in machine learning parlance. So cross entropy is negative of log of the estimated probability multiplied by actual probability of class 1 plus log of 1 minus estimated probability into 1 minus probability. 1 minus probability will be the probability of class 2. so on. So this is known as cross entropy, something we encounter very often in machine learning as well. Now, unlike linear regression, where we have a closed form solution for the betas, we do not have a closed form solution here. So we use numerical algorithms in order to estimate these parameters, beta naught, beta 1, and so on up to beta n. So we'll get those betas using some numerical algorithms. Gradient descent is something that can be used to get these. Now, once we have got these coefficients, what is the interpretation of these coefficients? The individual coefficients are in log units, so they are not directly interpretable as they are in the linear regression, where each of the betas is the rate of change of the outcome with respect to that x variable, given everything else is constant. Here, beta is the change in the log natural of the odds ratio, or alternatively, odds ratio is the exponential raised to the linear combination of each of these betas. So the interpretation of the coefficient goes as, if we have a positive beta, this means that as that particular variable x increases, the probability of the outcome also increases. If beta is negative, as x variable increases, the probability of the outcome decreases. And how much is given by that particular logit function. Now, if you want to classify based on the probability outcome, we want to say whether it is a pass or a fail or a success or a failure. We can have some kind of a threshold, typically p equal to 0.05. Anything greater than that would be termed as a success, and anything less than that would be termed as a failure. So once we have these betas and the model is created as well, we need to look at the overall model and how good it is. So there are some common model diagnostics for logistic regression. We'll talk about a couple of them. The first one is the omnibus test. In the omnibus test, we are looking at the statistical significance of the overall model. So this is similar to our F test for multiple linear regression. So here the null hypothesis is that all the betas are equal to 0. And the alternative hypothesis is not all betas are 0. What we do in omnibus test is calculate this particular term negative to log of the ratio of log likelihood of model with no variables divided by the log likelihood of that particular model with all the variables. This particular term comes out to be a chi-squared distribution with a degree of freedom of 1. So we can calculate the p-value and then from that infer the overall statistical significance. Wald's test is to look at the significance of the individual variables. So here are null hypothesis that beta I equal to 0, and the alternative hypothesis is that beta I is not equal to 0. We calculate what is called the Wald statistic. Wald statistic is given by the ratio of beta divided by the standard error. And again, this comes out to be a chi-squared. We can calculate the p-value. If p-value is less than 0.05, the variable is significant. Most of the common softwares will give us these results of these tests, omnibus test and Wald test. In Python and R as well, we can get the output of these model diagnostics. So we can look at that to understand whether our logistic regression model is statistically significant and which variables to keep there. Another thing we want to do is understand how good the model is. So kind of like looking at the accuracy in terms of what we did with linear regression. One of the tests which does that is to check the goodness of the logistic regression is Hochsmer-Lemischott test. This is again a test which is available in many of the open source softwares, as well as some of the licensed softwares like SAS and SPSS. Now, to look at the overall goodness of it or the accuracy, it's not possible to calculate the R squared the way we do it in linear regression. However, there are certain alternatives, pseudo R squared, this called the Cox and Snell's R square and Nagelkeker's R squared, which are available, and those could be calculated for a logistic regression. Another way to look at how good a logistic regression model is to look at the percentage of concordant and discordant pairs. So that's a way. We'll not go into any of those, but this most common thing to do is look at the ROC curve, or what is known as the receiver operating characteristics. That is what we'll talk about in this. Um, and before we do that, let's look at some of the other terms. So as we said, we'll use logistic regression for classification based on the probability of greater than 0.5 or less than 5.5. We'll term that as true or false. Is this the right approach? So before we answer that, let's look at some of the classification metrics. Uh, when we use a model to classify things, we can come up with a table like this. This is known as the confusion matrix. So we will have the actual output, the truth, which is a true or a false or a 0 or a 1, and then our model predictions with the given threshold probability of PC. This could be classified as a true or a false. Now those data points where our model predicts it to be true and it's actually true, this is known as true positive. Those where it is a true but our model predicts it to be false, this is called false negative. One of the important metrics we look at is called sensitivity. So sensitivity is true positive divided by the total number of actual positives, which is true positive plus false negative. This is an important metric to look at. The other way is also the false positives and true negatives could be defined similarly, where it's actually false but our model says it is true, then that's a false positive, and if it's actually false and our model also says it is false, that's a true negative. So here another metric which is defined as specificity, which is true negative divided by true negative plus false positive, which is the total number of actual negatives. There are a few other things. Accuracy, as we know, is very common. So accuracy is defined as how well we have been able to classify it correctly. So that's a ratio of the true positive plus true negative divided by the total number of positive and total number of negative, or the total number of data points themselves. We talked about sensitivity. It is also known as recall. And then another term we define is precision. So precision is true positives divided by true positive plus false positive. So everything is positive here in precision. Recall and precision are commonly used for information retrieval problems, but I have seen them being used in classification problems as well in machine learning. Depending on the business situation, accuracy may not always be the only metric to look at. So we look at some of these other metrics, sensitivity or specificity or precision, because sometimes it may be important to avoid a false negative or avoid a false positive in case of, let's say, machine failures, or drug sensitivity to a person and so on. Those may be more important rather than just the overall accuracy. So depending on different situations, you can use recall or precision. If you want to have some kind of a balance between those two, a score called F1 score is used, which is the harmonic mean of precision and recall. And that is given by 2 times the product of precision and recall divided by precision plus recall. So we have talked about this. Now let's talk about the ROC curve, or receiver operating characteristic. This is a way to determine the goodness of our model. So we talked about logistic regression. We talked about how the threshold itself can change our overall accuracy and precision and recall. Now let's say we change this threshold probability as shown in the table here, make it 1 and then 0.9, 0.8 and so on, and then we can calculate the true positive rate and the false positive rates, which is shown in the 2 columns in the table here. Once we have done that, we can create charts from that particular information. So we can have the probability cutoff values on the x-axis, and we can plot the sensitivity or the specificity on the y-axis. The ROC curve is where we plot the sensitivity on the y-axis and 1 minus specificity on the x-axis, and that curve is shown as the blue line here. The area under this particular ROC curve is known as AUC, or area under the curve, and that is a measure of the overall goodness of the model. The higher this area is, the better the model is. For a perfect model, we'll have the AUC score as 1. For a model which is no better than random chance, which would be the diagonal line, the AUC will be 0.5. Also, this ROC curve can help us get the optimal cutoff probability, and that is known as Udens index, and we'll see how to get it. One way to get it is visually, the other way is we can calculate those values from the table shown below. So Udens index, or the J statistic, is defined as that particular cutoff probability which gives us the maximum of sensitivity plus specificity minus 1. In the ROC curve, this is that particular point which is closest to the left top hand corner, or the point which is farthest away from the diagonal line. That's the cutoff probability. So if we take that cutoff probability, that will be the optimum cutoff probability. Another thing to look at is the gain and lift chart. So if we have the data which is highly imbalanced, then gain and lift charts are very, very helpful. Let me explain it by use of this table here. So once we have built the logistic regression model, we are satisfied with all the diagnostics and so on, then we can predict the probabilities or estimate the probabilities of all the cases and then order them by in a decreasing order or in descending order. And then for each of the deciles, we can look at the total number of actual responses as well as what is predicted by our model. So once we do that, we can come up with a table like this, where the first decile we can look at the total number of positive responses and so on. And this is typically used in marketing analytics, where you want to send out these different campaigns to customers, and then you want to know how many customers will respond back and so on, right? So you'll calculate all of these from historical ones. The percentage of events which is given for that particular decile divided by the total number of positive responses, that is known as the gain for each of the deciles. And the lift is the ratio of gain to the percentage of random expectation for that particular decile. So for the first decile, that random expectation is 10%. For the second decile, that random expectation is 20%, and so on. So the lift for the first decile here sorry, excuse me, will be 44.71 divided by 10. The second one will be 80.67 divided by 20, and so on. And then we can also draw these gain and lift charts and then visually communicate that to our stakeholders to show how good our logistic regression model is. All right, so we have talked about this. Now, one important thing to also look at is variable selection in logistic regression. Typically, what I used to do earlier was throw in all the different variables into the model and then just build the logistic regression. But that is not correct. There are methods to do proper variable selections, and we'll talk about two of them. One of them is the forward log likelihood. So in here, what we do is we calculate the log likelihood of the model without any variables, and then with each of the independent variables, one by one, we'll calculate -2 log likelihood. The model which has the maximum difference between the -2 log likelihood of the model with no variable and with that particular variable, that is the variable that will be picked in the first stage. Then we move to the next stage, where we'll have two variables at a time, and then we'll look at the difference between the second step, -2 log likelihood with two variables and -2 log likelihood with one. Where the difference is the maximum, we'll take that one, and so on. And we keep on repeating these steps till either we exhaust all variables, or we'll stop at a point where we see that adding a new variable is not impacting our log likelihood, or maybe the omnibus test or Wald statistic is coming out to be negative. Another way to do it is using forward selection with Wald statistic itself instead of calculating the log likelihood. So what we do here is we create the logistic regression model with one variable at a time in the first step, and we calculate the Wald statistics for that particular variable. The one variable where the Wald statistic is the highest, we pick that particular variable in the first step. In the second step, along with that variable, again we'll pick one more variable and then again calculate the Wald statistics. Here again in the second step, whichever model has the highest Wald statistic will pick that particular model, and so on, and we'll continue this process till we exhaust all of the variables. Along with that, doing an omnibus test is also important to see that the overall model is significant. So having talked about that, that is, the overall theory around logistic regression. Logistic regression could be done very, very easily in Python. It's just a few lines of code. There are two packages which are very popular. One is the stats models package, which gives you a lot of statistics around the model diagnostics as well around these models. So here, as you can see, it is very, very easy. You import these packages, stats models.api, and then you get the data. You create the model as sm.logit will be the model, and then you call the fit function to fit this. If you want to penalize some of the betas, then you can call the fit underscore regularized. And then finally, we can evaluate the models and see how good those models are and look at the confusion matrix and the result summary and so on. Another package, which is the famous sklearn package, this can also be used here. It's logistic regression is in linear model. We get the data, then we create the model. We have to provide some kind of a solver here. There are multiple solvers. One of the solver I've used shown here is liblinear. Then you call the dot fit function to fit the model and then evaluate the model. Look at their confusion matrix, and the overall classification report will give you precision, recall, and so on. And then you can keep on changing your variables and so on, and then have a good logistic regression model. So I hope that was useful. The next step in logistic regression is also looking at multinomial logistic regression, where we don't have just two output or two classes, but we can have multiple classes, could be 10, 15. As an example, let's say we want to run a marketing campaign to target people who want to look at a specific genre of movies, and we want to show those movies. So we want to predict which person will like what kind of a genre. This will be a classical multinomial regression problem, and we can solve this using multinomial logistic regression. However, I will not do it in this video, but this is something which we'll try to do in the near future. So with that, thank you so much for listening. I hope this was helpful. Again, I am Sachin Kumar, co-founder of Accelerate AI. Do check us out on Accelerate AI on LinkedIn. And if you have any questions, do write to us on accelerateddatascience@gmail.com. Thank you so much.